So this quiz contains 5 different integrals for you to attempt, all of which involve trigonometric functions, and the idea is for you to write them down, pause the video and try to solve them, and then afterwards you can, on the next slide, check if you've got the answers right, and if you have, well done, and if not, you can move further on into the video to explore the detailed answers to each of the above integrals. So with that, I would suggest you write down what's here and pause the video. Welcome back. So let's go and look at the answers. So here are the answers to the integrals. This integral here you can do by recognizing that this number here is odd. This is done by using an angle formula for the cosine of a plus b and the cosine of a minus b. You could also calculate it using integration by parts twice. I think that's more complicated and the answer will not look exactly the same, but of course it is if you put some work in to rearrange it. This integral can be done in different ways. The easiest way is to recognize that here we have the derivative of this factor. In a similar way, this integral can be calculated by recognizing that this is the derivative of the argument of the logarithm up to a minus sign, and it could also be done using integration by parts, and that would also work. And this integral here is calculated by recognizing that we know how to write sine of 2 theta as 2 sine theta cos theta, and then it is quite straightforward in a similar way to the first of these integrals. So with that, the rest of the video I will just go through the answers to the integrals in detail. So in this integral we have a product of sines and cosines, and if both powers are even we would use a double angle formula. However, one of the powers here is odd. So therefore what we do is we write our integral as the integral of sine of theta. We just pull out one power of sine times sine squared, and I'm immediately going to write sine squared as 1 minus cos squared of theta, multiplied by cos to the fourth of theta, integrated with respect to theta. So now in the next step I just multiply the cos to the fourth in here and here, so that's going to give us cos to the fourth minus cos to the sixth, and both of those terms are multiplied by sine theta, so we have got two integrals. So let me just write down what we have. We have the integral of sine of theta times cos to the fourth of theta, integrated with respect to theta, minus the integral of sine of theta times cos to the sixth of theta, integrated with respect to theta. And both of these integrals can be performed with a simple substitution, or in my opinion more easily with integration by inspection. So if we just look at it, we realize that this is the derivative of cosine. We have cosine to the power of 4, so if we had cosine to the power of 4 plus 1, cosine to the 5, when we differentiate it we'd bring down a 5, we'd reduce the power to 4, and we'd multiply by the derivative of cosine, which is a minus sign. So to get that right, what we can say is that our first integral is going to be cosine to the fifth of theta, roughly, and now let's imagine if we differentiate it, as said, we would bring a 5 in front, and we don't want that, so let's put a 1 over 5 to cancel it, and then when we differentiate it we'd have a cosine to the fourth that we want. We would have to, from the chain rule, multiply by the derivative of cosine, which is minus sine, and we want the sine, but we do not want a minus sign in front of it, so therefore we have to put a minus sign here. And in a very similar way, and being careful with the minus signs because there is an extra minus sign out front here, what we have is plus 1 over 7 times cosine to the seventh of theta. So we've calculated both of the integrals, and we can put on an integration constant, and this is our result for the integral of sine cubed theta cos to the fourth of theta, integrated with respect to theta. So with that, we'll move on to the next integral. So in our next integral, you could use integration by parts, but you would have to use it twice. So having used integration by parts once, this integral would turn into something plus the integral of sine of 3 theta times sine of 4 theta with some numbers in front. And then you would have to use integration by parts again, and you would then get back to your initial integral, take it back over to this side and have an equation that you could solve. So you can do it that way, but it is more complicated than it needs to be. So this integral here, what we have is the cosine of 3 theta times the cosine of 4 theta. So the formula that involves cosines multiplied by cosines with slightly different arguments is the following. So let's recall that the cosine of a plus b is the cosine of a times the cosine of b minus the sine of a times the sine of b. And therefore, by symmetry, the cosine of a minus b is the cosine of a times the cosine of minus b, and the cosine of minus b is by symmetry cosine of b, and then we have the sine of a times the sine of minus b, but the sine is an odd function, so we get an extra minus sign, and that makes this plus. So this is our formula, and both of these equations involve a cosine multiplied by a cosine. And to get rid of the sine times the sine, all we have to do is add these two equations, and they will cancel, and this will double up. So therefore, adding yields that the cosine of a times the cosine of b is going to be 1/2 cosine of a plus b plus the cosine of a minus b, close brackets, close brackets. So now we can take this result with a being 3 theta and b being 4 theta, substitute it into here, put it into the integrand, and this is going to be easy to integrate, and so will this be. So substitute a is equal to 3 theta and b is equal to 4 theta, and we have that the cosine of 3 theta times the cosine of 4 theta is 1/2 brackets, the cosine of 3 plus 4 is 7 theta, and then we have the cosine of 3 minus 4 theta, so that's the cosine of minus theta, but the cosine of minus theta is, by the even nature of the cosine function, cosine of theta. So the cosine of minus theta is cosine of theta, and it's much to be recommended to never write things like cosine of minus theta here and try to integrate that, because that's just extra minus signs that are going to get things wrong. So this is now something we can substitute into our integral. So putting this into the initial integral tells us that the integral of the cosine of 3 theta times the cosine of 4 theta integrated with respect to theta is 1/2, we'll pull it outside the integral, cosine of 7 theta plus the cosine of theta integrated with respect to theta, and that is 1/2 open brackets, and then we're going to put here sine of 7 theta, and if we differentiate that we'll get 7 cos 7 theta, so we put a 7th in front, and then here we have just plus sine of theta, because if you differentiate that you get the cosine of theta, close brackets, plus an unknown integration constant. So this is our result for the integral. And as I say, you can do it by integration by parts twice, but I think this is a far simpler way of doing it. So with that, I'll move on to the third integral. So this integral can be calculated in various different ways, and I think the easiest way is just to recognize that this factor here of sec squared phi is the derivative of the tangent of phi. So if you were to have the tangent of phi to one larger power and differentiate, you would get something like this. So let's just see what it would be. The tangent is to the power 1, so let's say that we had tan squared phi. If we differentiate it, what we do is we bring the 2 down, and we don't want that, so let's put a factor of a half in front. Then we reduce the power by 1, that gives us a tangent of phi, and then we would multiply by the derivative of tangent, and that is sec squared. So this is exactly the right answer, except we need to add an unknown integration constant. One could calculate this in other ways. So one could also use integration by parts, and if you say that v prime, the term we're going to integrate, is sec squared phi, and u, the term we're going to differentiate, is the tangent of phi, you will find the integral is not very difficult. You quite straightforwardly get back to the initial integral, and on solving the equation for the integral you'll find this result immediately. Perhaps it's also interesting to try to do it in a different way. So another way would be to say, why don't we write our integral as sec of phi times sec of phi tan of phi. I'm going to put brackets all around those last two terms and then integrate this with respect to phi. And the reason I've written it this way is that the derivative of the secant function is the secant times the tangent. So this is actually very, very similar to this. Here we had the tangent multiplied by its derivative, and that told us how to integrate it as a half tan squared. And now what we have is we say, we could write it as the secant times the derivative of the secant. So therefore, in a very similar way, we could say that our result is going to be sec squared phi plus an integration constant. And if I differentiate this, I'll pull a 2 in front, so let's put a half to cancel that. And then we would be left with sec to the power of 1, which we want, multiplied by the derivative of sec, which is sec tan, and that's what we wanted as well. So now we have these two results, and they look a little bit different, but this is actually nothing to worry about at all, and the difference in the two results is just due to the uncertainty in the integration constants. So the difference in the results for the two methods is hidden in C. So when we write these two results down, there's no reason for the integration constants to be fixed or even the same at all, and we just remember that sec squared phi is tan squared phi plus 1. So if we were to take this and put it here, we would have a half tan squared plus c plus a half. So that's just an uncertainty in the integration constant. So with that, let's move on to the next integral. So when we look at this integral, the integrand looks a bit complicated, and you might be tempted, and it does work, to try to use integration by parts. And if you do that, you would integrate this and differentiate this to get rid of the logarithm, and that technique works. There are, however, several powers of minus signs that you need to be careful with to make sure you get the right answer. So what I'm going to do instead is to say, let's use a simple substitution. And the formula that we are trying to recall is that if you have got some function of u of lambda, and this is multiplied by du d lambda, and then integrated with respect to lambda, you can calculate this just by taking your function f of u, integrating with respect to u, and at the end replacing u by u of lambda. So this integral falls into this format because here we have a logarithm, that's f, of the cosine, that's u, of lambda, and we have this factor here, just like here, it doesn't matter which side you write it on, of du d lambda, and if u of lambda is the cosine, du d lambda is minus sine, so we just put in a minus sign here and a minus sign in front. We have exactly this format. So this therefore tells us that our integral sine of lambda log of the modulus of the cosine of lambda with respect to lambda is minus the integral, the log of u, and now integrated with respect to u. And the minus sign is there because du d lambda is minus sine of lambda. And let's write down explicitly what we have with u equal the cosine of lambda, and du d lambda is minus sine of lambda. Now, the integral of the logarithm of u can be calculated using integration by parts, and because it's quite common, it's also a good integral to know. So let me just write it straight down. The integral of the sine of lambda times the logarithm of the cosine of lambda with respect to lambda is minus, that's outside, brackets, and now it is u log of u minus u close brackets plus some unknown integration constant. And u was the cosine of lambda, so we therefore conclude that the integral of the sine of lambda times the logarithm of the modulus of the cosine of lambda integrated with respect to lambda is. Now, here we've got a common factor of u, cosine of lambda. I'm going to pull it outside, and we've also got a minus sign multiplying everything, so I'm going to write this first, which is the positive term, and then subtract this from it. So we have the cosine of lambda, that is our term in front, times 1 minus cosine of lambda log of the cosine of lambda, close modulus, close brackets, plus an integration constant. And this is something that you can check straightforwardly by differentiation, and I would recommend that you do that. As said, you can also get exactly this result by using integration by parts and integrating that and differentiating that. I think personally this is an easier procedure. Okay, with that I want to move on to the next integral. The final integral here involves an integrand where we have the sine of 2 theta times the cosine of theta raised to a power. So the arguments of the trigonometric functions are different. And this integral, when we look at it, it suggests rather naturally to try to use the double angle formula for the sine of 2 theta. So let's remember what that is and just write it straight down. So the sine of 2 theta is 2 sine theta cos theta, so the factor of 2 will multiply everything, so I'm going to take it outside of the integral, and then we have the sine of theta times the cosine of theta but the cosine of theta is going to be multiplied by 3 more powers of the cosine of theta. So I'm going to write down immediately the cosine to the 4th of theta integrated with respect to theta. And now this is very much like the first integral we did. It's something we can do by inspection. So this is going to be 2, and then it's going to be the cosine to the power of 5 of theta. And if we differentiate this, we will put a 5 in front, which we don't like, so let's divide by 5. And we would then, when we multiply by the derivative of the cosine, we're going to have a minus sign. We want the sign, but we don't want a minus sign in front of it. So let's immediately put minus sign here, plus an integration constant. So the key message in performing this integral is that knowing the formulae, the double angle formulae, and the formulae for things like cos A plus B and sin A plus B are very, very useful things to know. And with that, I will stop this video.